I'll begin with a word of prayer. So, Dear Father, we thank you for this day again. I thank you for this class and this opportunity we have just to meet and study your creation. Just pray that you would again be glorified in what we do, Lord. In your name I pray, Lord Jesus. Amen. All right, so let us look at the notes. So I introduced last class, of course, the Biot Savart law, right? And so the Biot Savart law is essentially the, oh man, I didn't bring my markers. I guess I'm stuck on the projector. Well, I got one marker, so we'll see. It's okay. I can go back to my office if I need to.
Here's a black one if you...
Oh, thank you. That's okay. Thank you. Okay, so the Biot Savart law is the analog of like Coulomb's law, right? It tells you if you have a current, then you generate a magnetic field, right? And it tells you how to figure out the formula for the magnetic field by chopping up the current into little bits and then integrating, essentially. So we integrate along the current, not this equation here, but the one down a bit more. We integrate over the current to find the magnetic field. This would be analogous to what we did at the start of the course. Come on. Hello. Let me go down. What we did at the start of the course, where we, added up the electric fields from the different point charge, due to the different Coulomb fields of the point charges, we took the integral of all of those to find the net magnetic field. In the same way here, we find the net magnetic field by adding up all the little magnetic fields that are given by each little bit of current. Right, this is the Biot Savart law. It is a little bit tough to do these integrals in general. We did this example last class. Remember, we worked out that for a current loop, the magnetic field at the center is just, mu naught I over 2R. Now, this is the next example. Suppose you have a loop of current. Find the magnetic field at the point P due to this loop of current, all right? So R points from the current source to the field point, and then you take R and you have to cross it with DL. DL is the direction for the current. So if like the loop is like this, right? So my DL is like this, I cross into R, so my magnetic field is something like that. Well, it's hard to, you have to use your imagination. It's hard to draw 3D. But anyway, of course the magnetic field should be perpendicular to both the DL vector and the R hat vector because that's the geometry of the cross product. As such, we apply the Biot Savart law here, and we have this, which in this context gives me mu naught I dl over z squared plus r squared. Why z squared plus r squared? Because z is the distance from P to the center of the ring, and r is the radius of the ring, right? So the distance from the current segment to the field point is this square root, but then we square it, so we get that. Now we have to do what? Well, we have to integrate, right? You have to integrate. Notice that by symmetry, only the non-zero component is going to be in the z direction, because as you go around, the part of the magnetic field which is in the other directions is going to cancel out from different sides. And so I just calculate the z component, which I can get from sine theta times dB. Let's see the angle here. So let's see here. So that's my theta. So sine theta times dB picks out the, wait a minute, what? Huh. I don't think that's the right place to draw theta, guys. It's not right. It's not right. I think the theta, well, boy. I may have to go back to my office and get the markers. Well, let's see where this goes. I say sine theta is r over z squared plus r squared of z squared plus r squared. Does that comport with my picture? Yeah, it sure does. I really do believe in that theta. I just don't see, can you guys explain it to me? Why would that give me the z component? Yeah, it sure does feel like it should be a cosine to get the z component. I must not be... That is not cool. All right. Golly. It's a three-dimensional problem we're having here. See if I can figure it out. So if this is the ring, right, and I've called that theta. Now theta is constant all the way around, right? So I'm just going to draw it here for the sake of specificity. So imagine that the ring is coming out of the board at you, okay? So the ring's coming out of the board. So I'm drawing it like this, but to be more honest, I would just draw it like a line, because I'm thinking the ring comes directly out of the board and the current is like that, all right? So in that context, and I called this theta, and so this is r, this is z, and so the hypotenuse, of course, is the square root of r squared plus z squared. All right. Now let's try to work out the direction of things. So this is where we're calculating the magnetic field right here. All right. And at the moment I'm focused on just a little current segment right there. All right. So that is coming right out at you, right? Right out at you. And we're supposed to say dB is what? Mu naught over 4 pi. Mu naught I over 4 pi. Golly. dl. What did I use there? Unit vector? All right, fine. Crossed with r unit vector. So that just gives me the direction here. That's a unit vector direction divided by r squared. All right, so this is r. So r hat is like this, right? Agreed? So we do dl is straight out at you, right? Crossed into r hat, so that makes dB like this. I'll draw it big. There's your dB for this specific current segment. All right? So if I was to continue this line right here, I don't know if that's going to be helpful or not, but my line's kind of dipping down. Sorry about that, but we want this component. So dB has two parts, right? It's got this part and that part. So we're interested in this right here, which is BZ. Or you might say DBZ. DBZ. I'm a simple man. Anyway, so I think this is also theta, isn't it? Oh, so that one's, this is theta up here? Ah, okay, yeah, because that's complement. Yeah, very good, very good. Thank you. So we agree that's theta. And if that's theta, then dBz is what? Well, it took us a minute, but it's dB times sine theta, which is what I found so mystifying about 3 minutes ago, right? So my notes are right. Woohoo! It is, in fact, sine theta dB that gives us the z component. But admittedly, this is something you should really work through, right? Because these pictures, once you step away from them for like 10 years and come back to them, sometimes they don't make sense. Even though you drew them, you know? It's just hard to picture dB. So that's why maybe it's good to specialize and just focus on something that you have complete two-dimensional control over for making the picture to sort things through, yeah? That's what I do if I get confused anyway. So there it is. Now, once you have that, then that's the magnetic field that's contributed by that little current segment. But the thing is, the geometry is the same all the way around. There's nothing especially special about this upper little tidbit of current, right? The same story repeats as you go around. It's always dB sine theta, and the theta is constant around the ring, right? So we need to integrate this, this contraption right here, but I think everything's constant, right? The R and the Z, everything is constant. So the theta just integrates to 2 pi, and lo and behold, we get Bz is mu naught I. Let me turn off the lights up here. Mu naught I r squared divided by 2 times this right here. What does this formula collapse down to if we put z equal to 0? What's that? Mu naught I over 2r. Does that make sense? I think it makes sense because that was our example we ended last class with, right? Which is just a ring where we're asking the magnetic field at the center point. Yeah? And notice that it's doing what I said. If you can imagine like gripping the ring, right? The magnetic field that's being produced points this way, like I said. But now it's a function of distance. The further you get from the ring, the smaller the magnetic field, right? That's what that formula says. Let's move on. Another example. Oh, here, look, I'm just explaining. This is what I just said. But this also gives us the formula for so here I'm looking, actually, here I'm looking at the other limit. I'm looking at the limit that we're very far away from the ring, right? So z is much, much greater than r. In that case, the r is essentially ignorable. And we just get mu naught I r squared divided by 2 z cubed. And so this is the magnetic field due to a quote-unquote the dipole field. All right? You might wonder, wait a minute, so we talked about the Coulomb field. That was also known as the, you could also call it the monopole field for the electric field. No one calls it that, but it's a single pole, right? The Coulomb field. Is there such a thing for the magnetic case? Like, is there a single magnetic charge? Does that even make sense? Something we should talk about. Because I would point out that this, if you look at the far field dependence, it depends on like the cube of the distance. This is the behavior we saw for the electric dipole. It depended on the cube of the distance, the magnitude of the field. And so this is analogous to that, and that's part of the reason that this is called the dipole field. But there it is. That's the formula for it in this case. Now, move on here. So, again, here mu is the dipole moment of the current loop. It's defined to be pi I times r squared. So it's the area times the current is what that is, IA. The area of the loop. Here's a picture, just to complete the thought, of the electric dipole versus the magnetic dipole. So if I was to draw a picture of the magnetic field, it's helpful to draw magnetic field lines, right? So field lines are the lines that align with the field, right? So the magnetic field, it points tangentially to these curves here, right? So for the current loop, the magnetic field's going right-hand rule, right? It goes up like that. That's where the magnetic field's going. If the current's going like that, the magnetic field created by this current goes like this. It encircles the loop like so. All right? And you can compare that picture to the electric dipole where we have pluses and minuses, right? The electric field from the plus to the minus like that, but then around it goes like that. But the overall pattern of the field is very much the same geometry, the dipole field. Now, another example that's important, but I'll try to go fast through these because we do find a much better way to derive these after this little story arc in the course. Kind of like once we found Gauss's law, we kind of forgot a little bit about things that came before it a bit, you know, because Gauss's law is way easier. There's an analog to Gauss's law we're going to get to today, so let's get to it. But first, I do owe you these derivations, so here they are. You know, So a solenoid is a wire wrapped around a coil. It's basically just a coil of wire, and there's a current flowing through it, all right? So the way this works is there's a magnetic field generated by each one of these loops, right? And so we just basically think about the examples we've already done. Each one of these loops creates a magnetic field, right? And which way do they go? Well, right-hand rule. So if you imagine the solenoid, right? If you have to grip it, point your fingers, wrap your fingers around the direction in which the current's encircling the coil, right? Your thumb points this way. That means the magnetic field inside the coil is going to be pointing to the right. And then when it's outside, it does that kind of loop around thing like we were just looking at. N is the number of turns for Z1 less than Z2. This is the so-called turn density, the number per unit length. We use a little n for turns per unit length. And I think I'm about to show you some horrible calculation. So here it is. Maybe it's not too bad. So the current, how many loops do I have in a little dz? At z, I've got dz prime. And the little bit of current that's flowing there is Ni dz prime. That gives me essentially the number of loops there. Just to explain the math here, the number of turns per length times the current times the length gives me the current basically. Well, it gives me the number of turns times the current, which is essentially the current. So that's in that little bit of dz prime. Anyway, so the magnetic field that's generated from that one stretch of the loops, right, is given by this using the previous calculation. You notice that we've got the z squared plus r squared to the 3/2, and then upstairs I've got mu naught and then the I terms. And so to get the total magnetic field at the point z prime, I believe. Well, no, I think at z. Well, just a second here. I'm trying to figure out where I'm. Give me a second. I've lost track of where we're calculating the magnetic field somewhere. I think we're calculating it. See, all of these questions. There's always two central questions you have to ask yourself. Where is the source currents and which field point are we looking at? Like, where are we trying to find the magnetic field? For my first example last class, it was the center of the loop, right? For this one, it was a point along the axis of the loop over here, right? So the question I'm trying to ask and answer at the moment is like, where are we calculating the magnetic field for the solenoid? So we should be able to figure it out from looking at the setup here. Let's see here. So I've got z prime, dz prime. I think z is fixed here, right? Z is fixed. And I think I'm trying to calculate the magnetic field at P. I'm trying to find the magnetic field at the point P in the solenoid. So I'm trying to figure out what's the magnetic field in the direct center point of the solenoid. That's kind of like the nicest possible point to calculate the magnetic field. I believe that's what I'm doing here. So that would make sense, because then see z prime, z minus z prime would be like the, well, then I'd have z equal to 0, right? So I think I'm just finding the magnetic field at a point z along the axis, actually. Yeah, it's worse than that. It's not as easy as I thought. So I got to integrate this monstrosity, which is not too bad. So after, what is that? That's just a kind of integrals that. Yeah, I think you're right. I think it is a trig substitution. So, so after a trig substitution, we have the fundamental thermal calculus part 2, we get this lovely formula right here. This is the magnetic field at z along the center point of the solenoid. All right, so then that's the magnetic field on the axis. I guess if I just scroll down, I have the answer right here. So the magnetic field on the axis of the solenoid. Now, if what? If L is much, much greater than R, what would that mean? That would mean the solenoid is very, very long relative to its radius, right? So that would be a very long solenoid, which would mean that all of that like wraparound stuff is like way, way out, you know? So inside a long solenoid, essentially the magnetic field's straight inside the solenoid. Now, if the solenoid is not as long, if it's shorter and the radius is big, then you've got the magnetic field lines like bending off the center because they do that loop around thing, right? But in this limit, they're essentially straight inside the solenoid. And we can look at what that formula does in that limit. And if you tilt your head and squint, goodness. In the center, you'll be able to show that that formula simplifies to just mu naught Ni at the center. And at the ends, it ends up being 1/2 of mu naught Ni. These are claims. It's not mathematically obvious, I don't think. What do you guys think? To go from here to there? I don't see it right offhand. I'd have to do some calculation to see that. All right, but if I don't do it, I can't hold you responsible for it, right? So let's go on. Another calculation that's important, well, important's too strong a term. Another calculation you should see, and I don't like this picture that much, but I'm not going to belabor it. There's a similar picture that may be better on page 952 of the textbook. They've got a picture of like a current segment, and they're calculating the magnetic field due to a current segment, but the picture is sideways of this one. Anyway, when you sort through the geometry here, so the question is, what's the magnetic field over there due to a current segment here? Of course, you could also put the field point like here. That would be more natural to me, but I put it over there for reasons I forget. But anyway, there it is. And so then you apply the Biot Savart law, and tilt your head, squint, the rest of it. Do the geometry, set it up. Let's see here. So the R makes sense because that's the distance from the source point where the current segment is to the field point where B is. That's R. So we've got that division by R squared. I dx, because that's I dl, because dx is the distance, is the direction along the line segment. The sine phi gives me the magnitude of the cross product, because that's a measure of, you know, for example, if phi is 90 degrees, then the cross product is just simply the product, magnitude of the cross product is product of the magnitudes of the quantities being crossed. So that makes sense. This phi being 90 degrees gives me 1. That would correspond to the case that we're calculating the magnetic field right up there. All right? Man, should have brought my laser. Oh well. I'm not going to get distracted. Now, this seems like some dark magic. Where's this cosine theta coming from? Well, look at the picture. I defined theta there, right? So, and anything else changing here, or just the cosine theta? I'm just swapping out a sine phi for a cosine theta. Does that make sense? They're complementary, so yes. All right, so this are equal because theta and phi, because of the geometry here, that makes them equal. Now, once you have that, you can also notice that x is equal to r tangent theta. Make that substitution, and then you can simplify that to get a secant theta, but also cosine theta happens to be r over r, which gives us that r squared is really big R squared over cosine squared, which, anyway, after you do the math here, you get mu naught I over 4 pi r cosine theta d theta. And then we have to integrate from theta 1 to theta 2. Now, theta 1 to theta 2 are back up in this picture, right? Theta 1 is this angle. Theta 2 over here, this angle. So integrating from theta 1 to theta 2, that's the setup here. Now, the setup in the book on page 952 is a bit different. And but this formula is pretty cool. So this is the formula for the magnetic field of a line segment of current. I will not get distracted. This is difference of the signs, all right? So we can think about some different special cases, right? Like if you're on the midpoint, I think those angles would be what? If you're right on the midpoint, what would happen? What if your B is like right in the middle? What would you? I think theta 1 would be what? Like, actually, can I even do that? I don't know if I can do that with this setup. I'm not sure I can move. Well, anyway, let me stop. So here's the deal. As theta 1 goes to minus 90 degrees and theta 2 goes to 90 degrees, what would those limits be? If we go back to let me go back to the original picture. What would it mean for the angles both to be going to like plus and minus 90 degrees? So you can look at it. What would it mean for like, if theta 1 is 90 degrees, what would that mean? Man, I can't picture it. I'm sorry, guys. I'm annoyed by this picture. But this formula down here is important. So if the theta 1 is minus 90 degrees and theta 2 goes to 90 degrees, the magnetic field we get is just mu naught I over 2 pi r. And we can see that the magnetic field wraps cylindrically around the wire as specified by the right-hand rule. I think, well, anyway, I'll tell you what, guys, I'll try to come back to this example in the Friday thing and see if I can fix it. I'm not happy with the picture right now, but I kind of need to go on. So the last page in here, and so I'll talk more about this as we go on here today, but just to give you story here. So if we think about two parallel currents, right? You can imagine the magnetic field circling around both by the right-hand rule. So the magnetic field created by a current, we point our thumb in the direction of the current, and then our right hand wraps around in the direction of the magnetic field created by that current. So like current 2 creates magnetic field B2 over here. See that? Over here, it's going down into the page. So the magnetic field created by current 2 is B2, it's going down. Vice versa, though. If I think about current 1, right-hand rule, right? And then think about my thumbs coming up here and hitting where I1 is. It's hard to, I need to draw a different picture, but anyway, we'll deal with this one for now. The magnetic field due to 1 is going up, right? So we can think about then what's the force of the magnetic field of current 2 on current 1? Remember, the force is what? IL cross B, right? So if I do I2 crossed into B1, which direction does the force go? I2 crossed into B1, force is that way. How about I1? I1, right? I1 crossed into B2, the forces are going that way. So the force on the first current is going this way. The force on the second current is going that way. What's that mean? They're being drawn together, right? So parallel currents attract each other. Yep. Oh, that wasn't a question. That was a right-hand rule. Okay, good. So that's good. I like to see people doing the right-hand rule. Sometimes you look at like a test for electromagnetism or the later part of physics 1, and you see people trying to do the right-hand rule like subtly, so other students don't see it, because it might not be cool to be seen doing the right-hand rule, you know, something like that. But now this is really good news. This means that if you have two currents that are close by, that they create magnetic fields that influence the other current close by to do what? It tries to draw the wires together, right? On the other hand, if the currents are going in the opposite direction, you'll find the opposite thing. You'll find that those opposite currents try to force each other apart. Why would this be important, for example, for circuitry? What if you have like a big wire that's formed by lots of little wires close to each other? Basically, that's what it is, right? You have like not a solid core, but you've got a bunch of little cores and they're just together. Well, in that situation, if they were to somehow get separated, if there's a lot of current in them, then they're naturally drawn back together by this phenomena. So like it has the tendency to keep wires together. Anyway, it's kind of neat. So parallel currents attract. If I reverse the direction, they repel, is the answer to that. And we can look at the force per unit length by that calculation right there. So like the force per unit length ends up being the product of the currents divided by 2 pi r. Now I'll explain this more. Here I'm assuming something here, guys, which is that the magnetic field due to a very long wire is equal to mu naught I over 2 pi r, where r is the distance from the wire. All right? So if I had my act better together today, I would have convinced you with my pictures. I'm not happy with the pictures today. But the pictures would convince us that, in fact, this is the situation, that if we have a current, so let me turn the lights on in here. If we have a current, go away, be gone. So the summary, we've seen some complicated examples, right? In terms of the calculus. The calculus was kind of formidable, wasn't it? But long story short, if there is a current, let's say it's coming out at you, right? Then if you want to know what the magnetic field looks like, if that's a long wire, if it's a long wire, the magnetic field encircles the current. And so the magnetic field lines look like this. On the other hand, if the current was going into the board, all right, then, well, the field lines still look like circles, all right? But the right-hand rule says that they go the other way. So they go this way. So you might say that this is counterclockwise, whereas this is clockwise. And here I'm drawing the magnetic field lines, all right? Now, and this is only literally true. The formulas I'm about to write, they're only literally true. In both cases, B is equal to mu naught I over 2 pi r for very long wire. And that can be derived from the calculus that I butchered today, all right? Well, I don't think the calculus was so much butchered. It was really more the pictures that I'm bothered by, but I'll get over it. Let me try to redeem today by showing you the much easier way to do this. All right? And the much easier way to do this is with something called Ampere's law. So what is Ampere's law? Let's talk about it. So Ampere's law is sort of the analog of Gauss's law for magnetic fields. And in a nutshell, it says that it relates the current enclosed by a loop to the magnetic field. Let me write the symbols we usually use for it. So we can say that the integral around the curve of B, we try to use the same symbols I usually use in here, dl is equal to mu naught and IC. So let me try to explain this. So this is a loop, all right, and this right here is the current that cuts directly, let's say, through you know, the area bounded by C. All right. This is Ampere's law. So it relates the so-called circulation of the magnetic field, right, the line integral of the magnetic field, to the current enclosed by that. Now let me show you an example here. So example 1. I feel like my interpretation for these events is simple. I've been teaching physics a while here, calculus too. In the past, I'm sure I failed someone several times. I'm sure I had my reasons. This person feels slighted. Later, they got a job in IT. Now they find out where I teach, and they make these things happen. I think that's the most interesting explanation for these things happening. It could be haunted. My brother used to believe that there was a tragedy that killed a whole group of students in one room at NC State, and it left a stain of stupidity on the room, because every time he taught a course in there, the people were just dumb. Very, very dumb in that room. So, yeah. But as far as I know, the room's not haunted. Okay, so how about this? We have a super long wire. Super long current, to use technical terminology. And I'll make it go this way. All right? We are then going to, and by the way, this is not just any loop. To be sure, this is an Amperian loop. What's an Amperian loop? An Amperian loop is a loop that you apply Ampere's law to. Just like a Gaussian surface is just the same as a surface. It's just a surface you apply Gauss's law to, right? But an Amperian loop, if you're smart about it, you'll choose a loop which, well, you draw the loop first and then draw the wire second if you're smarter. But we're just going to make the loop. Let me draw a picture of it straight on. So it looks like this, you know? So here's my, I'll draw it as if it's into the page, all right? And I'm going to make this loop at distance r. Okay? What's the direction of the magnetic field induced by the current? Right-hand rule. Thumb points in the direction of current. Magnetic field lines loop around. So it goes like this here, like that there. That's behind the wire. I don't know how to draw that. Well, anyway, there, that's better. So if it's going in, my picture is going into the board, so my magnetic field lines go like so. All right. So in this case, what does dl look like? Right here, I'm trying to draw that tangent, but this is my dl vector, right? And like over here, these are supposed to be tangent. I tried. dl vector. All right? Those are what? Notice that dl is parallel to b all around the loop. Right? This loop is a circle, actually, to be clear. Do you guys see it? So, goodness gracious. I've got to zoom in. So if that's the case, how does that line integral work out? Like, what is a line integral? It does what? It calculates. So here, this circle here just means that it's a closed loop. That's just notation to emphasize what we're doing. But what does this work out to? In this special case, what's the line integral? If the vector field is parallel to the curve you're integrating around, right? B times the perimeter of the curve. What's the perimeter of a circle? 2 pi r. So this gives us b times 2 pi r for the loop considered at the moment. Right? Ampere's law says that that's equal to mu naught I enclosed, right? Sometimes I say I enclosed. Why am I working around this table? Like, what is this table? Like, do people teach in this room? Like, what is this? Oh, that's right. This is where the projector goes. So, if I was smarter, I'd just be projecting. Writing takes work. Projecting is just, oh, hey, thanks. So what's B? Notice that the current enclosed here is just I. What's the current that goes through the wire? Through the loop. I'd do another color if I had another color, but anyway, if you can imagine the surface is just the disk, right? That's a choice of the surface. There's something to think about. And so that's just I, and the magnetic field in this case is, mu naught I divided by 2 pi r. There you go. That is the magnetic field for a very long wire, a distance r away from it. This is much, much, much easier than direct calculation from Biot Savart and then taking some sort of limiting process, right? Yeah. It's so Ampere's law is important. This is our bread and butter for how to calculate magnetic fields. All right. Now example 2, let me make this one uglier if I have time. Yeah, I have time. What if instead of a line, instead of just a so I basically assumed, I ignored the what's the word, the internal geometry of the wire. I just assumed the wire is like a line, right? What if the wire is not like a line? What if the wire actually has like a dimension, like this, r, right? And then I can ask the question, what's the magnetic field inside the wire? Supposing the wire is very long. Let me blow this up. It's not big enough for my picture. This could be a really huge wire for the sake of illustrating the idea. And it's supposed to be very long, which is not really what I'm drawing. All right, but we've got a current I uniformly distributed over, let's say, 0 less than or equal to r less than or equal to big R. Then I can ask, what's the magnetic field? What's the magnetic field at distance r from the center line of the wire? Like, I know symmetry says what? If I drew a picture, let me just suppose that the it's coming out at us. So like this is, you know, my eye. Then if that's the case, then my magnetic field lines, they've got oh man, let me just shade it. So where's the current's actually flowing, right? So the field lines, they're again, they have to loop, just, you know, wrap around like that. My magnetic field lines. So it's pretty easy to see that the magnetic field outside of the wire is what? So like B is still mu naught I over 2 pi r for r greater than or equal to r, since I enclosed is just equal to I out there. Right? If I take a loop, an Amperian loop, which is not inside the wire, I enclose the whole current, right? But what happens if I take an Amperian loop that's like inside the wire? Right? So like here's just the outside of the thing for context. So like the question is how much current is enclosed here, you know? Let me draw it this way. So here's the outside of the wire, here's the Amperian loop I'm thinking about, all right? And I'm gonna make that at R. So my question is, what's the current enclosed there? I have a vote for I enclosed is equal to little r squared over big R squared times I. What do you guys think? I think that makes sense. It's the proportion of the area of the little circle to the big circle, right? I might put a pi above and below, but then you cancel it. So that's, you know, the pi's cancel. So there it is. And otherwise, the symmetry is the same, right? So we still have this, you know, Ampere's law, B dot dl over this loop, which I'm calling C apparently, is equal to mu naught I enclosed, but that gives me B times 2 pi r is equal to mu naught times little r squared over big R squared times I. And what's that tell me? That tells me that the magnetic field inside the wire is actually Stephen, you're doing this, aren't you? It's you.
What?
You did the lights. It's part of your trickery.
Yeah.
You did that with the cards. Now you're doing it with the lights. I know it.
What can I say?
I'm watching you. See here. So, sorry, I'm an idiot. Mu naught R I divided by 2 pi big R squared, I think. So this is for 0 less than or equal to R less than or equal to big R. Does that make sense? What happens when little r equals big R? How do these cases match up? Do they match up? Yeah. What I'm doing right now, this is the analog of the uniformly charged sphere, where we find Gauss's law by looking at a Gaussian sphere inside that, right? So here I'm looking at an Amperian loop inside the wire with a uniformly distributed charge. I mean, not charge, current. Notice how this works. It is equal to 0 at 0, so the magnetic field 0 at the center of the wire. And then it increases linearly all the way up to its maximum right at the edge of the wire of mu naught I over 2 pi big R. And then it drops off like that beyond the wire. So these are the probably two most important examples of Ampere's law, but we'll look at a bunch more. Well, the other really important example is the solenoid. We'll see how to do the solenoid with Ampere's law. It's going to be way, way easier. So I'm sorry to butcher Biot Savart, but you know, it's a tradition of mine. So thanks, guys.